US Physics Olympiad year 2020 USAPHO first round. Problem A3. Spin cycle. Cosmonaut Clara is preparing for the intergalactic 5000 race. She practices for her race on her handy race track of radius r, carrying a stopwatch with her. Her race car maintains a constant speed v during her practices. For this problem, you can assume that v greater than 0.1 c, where c is the speed of light. Question A. How much time elapses on Clara's stopwatch with each revolution? Clara decides to do a fun experiment during her training. She places two stationary clocks down clock A at the center of the racetrack, i.e. the origin, and the clock B at a point on the racetrack denoted as R0. She then begins her training. For parts B through D, we define Clara's inertial reference frame, CIRF, as an internal reference frame in which Clara is momentarily at rest, and which has the same origin of coordinates as the lap frame. Thus, CIRF is a new inertial frame each moment. The times on the clocks and the stopwatch are all calibrated such that they all read 0 in CIRF when she passes by clock B for the first time. Question B. In the lap frame, the reference frame of the clocks, which are at rest, what is the offset between clock A and the clock B? Question C. If Clara's stopwatch measures an elapsed time tau, what does clock A measure in CIRF? Question D. If Clara's stopwatch measures an elapsed time tau, what does clock B measures in CIRF? Solution for problem A3. Question A. How much time elapses on Clara's stopwatch with each revolution? Solution. From time dilation, her clock ticks slower by factor gamma. Therefore, each revolution takes pi r over gamma v, which is this expression, 2 pi r multiplied by square root from 1 minus v square over c square and everything over v. That's the answer for question A. Question B. In the lap frame, the reference frame of the clocks which are at rest, what is the offset between clock A and clock B? Solution. Clara's motion is perpendicular to the displacement between clock A and clock B when they are synchronized in CIRF. Therefore, the simultaneous synchronization in CIRF is also simultaneous in the lap frame. Thus, the offset is 0. To understand why this offset is 0, you can also imagine placing light bulb halfway between the two clocks and having it send a light pulse at some known time. In both Clara's frame and the lap frame, the light pulse reached the two clocks simultaneously. That was a solution for question B. Question C. If Clara's stopwatch measures an elapsed time tau, what does clock A measure in CIRF? By symmetry, the speed at which the center clock ticks according to CIRF cannot change. In one revolution, Clara's stopwatch measures this time tau, while the center clock measures 2 pi r over v. So it means then center clock measures tau over square root from 1 minus v square over c square. That's the solution for question C. Question D. If Clara's stopwatch measures an elapsed time tau, what does clock B measure in CIRF? Solution. The readings on clock B and on clock A are not necessarily identical once Clara moves through the circle, because her motion becomes more parallel with the displacement between the two clocks, and thus simultaneity is lost. Suppose Clara is at coordinates r cosine theta, r sine theta. So her velocity is given by negative v sine theta, v cosine theta. Suppose we place a light bulb between the two clocks and having it propagate a light pulse. In the lap frame, the light pulse reached the two clocks simultaneously. In CIRF, the math is a little more complicated. We first rotate our lap coordinates so that A equal negative sine theta x plus cosine theta y, and B equal cosine theta x plus sine theta y. We now give the coordinates of the clocks and bulb in the rotated lap frame like this. Clock A is 0, 0. Clock B is negative r sine theta, r cosine theta, and bulb negative r sine theta, r cosine theta over 2. In the lap frame, a light pulse is emitted at t equal 0, a equal negative r over 2 sine theta, and b equal r over 2 cosine theta. The light pulse reached the clock A at t equal r over 2 divided by c, a equal 0, and b equal 0, and clock B at t equal r over 2 divided by c, a equal negative r sine theta, and b equal r cosine theta. Under Lorentz transformation from the lap frame to CIRF, we have that the light pulse reached clock A at t prime equal gamma r over 2 divided by c, clock B at t prime equal gamma r over 2 divided by c plus gamma v r divided by c square sine theta. Thus, clock B reached the same time as clock A with the offset gamma Vr over c square sine theta in the reference frame, moving at Va equal V and Vb equal 0. Note that clock A ticks slower by a factor of gamma in this frame. Therefore, the time of clock B is Vr over c square sine theta behind the time on clock A. Then we have Tb tau equal Tba tau minus Vr over c square sine theta, or this expression. This is the answer we expect from the rear clock ahead effect. Finally, we use that theta equal omega tau and omega equal 2 pi over t, where t is the period in Clara's frame. Finally, Tb tau equal this expression, and that was answer for question D. And here we finished discussion for problem A3.